This is section 15.4. There are only 4 problems in the homework, but they could get really long, which is the reason why I only gave 4. Even though there's 4 problems, each one involves 3 integrals. So you're actually ending up doing 12. So I'll do several of the problems in this section. So let me go ahead and share the screen and see what's up. All right, so the topic is applications of double integrals. We're only going to look at center of mass, density, and mass involved. Okay, so we have an object. General object is sometimes called a lamina. So what is a lamina? It's just an object, right? It does not necessarily have uniform density. The density varies perhaps from point to point. Okay, so you could, of course, chop this picture up, chop the lamina up into so many pieces and analyze each one. Okay, but let me just give you the highlights of this. Right, so moments and center of mass on page 1017. Okay. Box number 3, you can put that in your formula sheet. M sub x, the moment about the x-axis is a double integral over the region D of y, rho of xy dA. So rho is the density function. Okay, so the density as a function of x and y at a given point. Okay, and likewise, the moment about the y-axis, m sub y, you can skip all this stuff. Just come over here, double integral of x, rho of xy dA. This might seem kind of counterintuitive, where m sub x you use y and m sub y you use x, but actually makes sense. We're talking about the moment or the tendency to rotate about the x-axis. So if you think of the tendency to rotate about, let's say, the x-axis at any given point, let's say over here, well, this distance is y. And likewise, if you're talking about the tendency to rotate about the y-axis, this distance that I'm pointing out is x. So that's the reason why you have that. So you multiply the density by the moment arm, as it were. Okay, so m sub x, double integral of y, rho dA, m sub y, take the double integral of x, rho of xy dA. And then, of course, if you just want the mass, you integrate rho. So the mass is a double integral of rho dA. And now that gives us the center of mass, x bar, y bar, formula on page 1018. Put this on your formula sheet. X bar is m sub y divided by m, the m sub y that we got from the previous page, or 1 over m, double integral of x, rho dA. And y bar is m sub x over m, 1 over m, double integral of y, rho of xy dA. So again, rho is a density function. This object does not have to have uniform density. In fact, in general, it won't. So the density changes from point to point. And you want to know what is the center of mass of the object, the theoretical points where if you were to balance it on a pen, straight up like on a piece of paper, it would balance perfectly on such an object, okay? So that's what we're up against. So for all of these problems to find the center of mass, you need to do 3 integrals. You're integrating rho, x times rho, and then y times rho. Okay, and then x bar is just m sub y divided by m, y bar is m sub x divided by m. Okay. And I decided not to give you any moment of inertia. There's nothing wrong with it. There are formulas there. Okay. But the whole idea is just kind of give you a taste of it. Okay, and there's some probability issues if we wanted to, but we don't want to. On page 1021. So here we go. So 15.4, we didn't have that many problems. So page 1024. 3, 5, 7, 9, and 11. Okay. All right, so number 3, rho of xy is ky squared, 1, 3 cross 1, 4. So the mass is a double integral of ky squared dx dy. X goes from 1 to 3, y goes from 1 to 4. Let's see, k is a constant, bring it out. This function does not depend on x, so take out the length of the interval of x, which is 2. So 2k comes out, integrating y squared dy. So 2k y cubed over 3 from 1 to 4, which is 2k over 3. 4 cubed is 64, minus 1 cubed is 1. 2/3 of 63 is 42, so the mass is 42k. Right, now for m sub x, I multiply this thing by y. So it's y times ky squared, or I'm integrating y cubed. Okay, a lot of the original part stays the same. Take out the k, take out the 2. This integral does not depend on x. So I just take the length of the interval, which is 2. K comes out, and I'm integrating y times y squared, y cubed. Okay, so 2k y to the 4th over 4 from 1 to 4. This becomes k over 2. Plug in 4. 4 to the 4th is 256. Plug in 1, you get 1. 255k over 2. M sub y, I multiplied the original density function by x. So integral from 1 to 4, 1 to 3, k x y squared dx dy. This one is not a constant as far as x is concerned. So integral is k x squared over 2 y squared as x goes from 1 to 3. Take out the k over 2, leave the y squared alone. Plug in 3, you get 9. Plug in 1, you get 1. So that becomes 8. 8 divided by 2 is 4. So 4k integral y squared dy. So 4k y cubed over 3 from 1 to 4. 4k over 3, plug in 4, you get 64. Plug in 1, you get 1. So 4k over 3 times 63. 63 divided by 3 is 21 times 4, 84k. All right, so we did our 3 integrals. And now x bar is m sub y divided by m. M is 42k, that's on the bottom. And we just got 84k for m sub y. So 84k divided by 42k, 2. Then y bar is m sub x divided by the same m, so 42k stays in the bottom. And the numerator is m sub y. We got that to be 255 over 2, somewhere over here. 255k over 2. Okay, this 2 is allowed to slide down with the 42. So 255k over 84k reduces to 85 over 28. Okay, so the question asks, what is the mass? 42k. And the center of mass is 2 comma 85 over 28, a little bit more than 3. That's the center of mass for this lamina, this object. Okay, so that's the basic idea. Okay, 7, y equals 1 minus x squared, bounded by y equals 0. Rho of xy is ky. So the mass is integral from -1 to 1. Y equals 0 to 1 minus x squared of ky dy dx. So k y squared over 2 from 0 to 1 minus x squared dx. Plug in 0, you get 0. Take the 2 out. And plug in 1 minus x squared. 1 minus x squared dx. Okay, and so this comes out to be, it's an even function. So if I integrate an even function, I can just integrate from 0 to 1 and double my answer. 1 minus x squared is x to the 4th minus 2x squared plus 1. So the 2's cancel out. So k, x to the 5 over 5 minus 2x cubed over 3 plus x from 0 to 1. Plug in 0, you get 0. Plug in 1, 1/5 minus 2/3 plus 1, which is k times 3 minus 10 plus 15 over 15. And that comes out to be 8/15 k. All right, m sub x. So integral from -1 to 1. And y goes from 0 to 1 minus x squared. Okay, so the original was ky. I have to multiply by an extra y, so ky squared dy. So that's y cubed over 3. Plug in 0, you get 0. Plug in 1 minus x squared. I got 1 minus x squared cubed. Okay, that's a little bit messy. You could use Pascal's triangle, 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. So you can go 1 cubed, 1 squared, 1, and 1 to the 0. Negative x squared to the 0, negative x squared to the 1, negative x squared squared, negative x squared cubed. and the coefficients are 1, 3, 3, 1. Okay, so if you work that all out, let's see. Again, I had an, yeah, this is an even function. So I integrate from 0 to 1 and multiply by 2. So 2k over 3, multiply all this mess out, comes out to be 1 minus 3x squared plus 3x to the 4th minus x to the 6th. Okay, so integrate x minus x cubed plus 3x to the 5th over 5 minus x to the 7th over 7 from 0 to 1. Plug in 0, you get 0. Plug in 1, 1 minus 1, that's nice, plus 3/5 minus 1/7. These are gone. 2k over 3. Common denominator here is 35, so 21 minus 5 is 16. So 32k over 105. M sub y, I multiply by x. So k, xy, dy, dx. Same limit, same limit. So k, x, y squared over 2 from 0 to 1 minus x squared. So that's k over 2, x times 1 minus x squared squared. That's going to be an odd function. Okay. If I replace x by negative x, I get the opposite. And you might recall anytime you integrate an odd function from negative a to a, your answer is automatically 0. Okay. A good example is y equals x cubed. If I integrate from negative 2 to 2 or negative 5 to 5 or negative 1,000,000 to 1,000,000, you get just as much on this side as that side. So the answer is automatically 0. So I don't have to evaluate this. This is automatically 0. Okay, so x bar is m sub y over the mass. That's automatically 0. Y bar is m sub x, 32 over 105k, divided by the mass, 8/15 k. K's cancel out, so 32 over 105 times the reciprocal of 8/15, 15/8. That reduces to 4/7. So the mass is 8/15 k, and the center of mass x bar, y bar, 0, 4/7. Okay, finally, 11. X squared plus y squared is less than or equal to 1. First quadrant, y equals radical 1 minus x squared. And the density is proportional to the distance from the x-axis. The distance away from the x-axis is y. So in other words, rho is ky. So the mass is double integral over the region R of ky dA. This looks very convenient to switch to polar coordinates. So I do. So ky is r sine theta. K comes out. Don't forget to multiply by the extra r when it's dA, r, dr, d theta. R goes from 0 to 1. Theta goes from 0 to pi over 2. K is outside. So I have r times r, or r squared. So when you integrate, it's r cubed over 3. R equals 0 to 1. Plug in 0, you get 0. Plug in 1, you get 1/3. Take the 1/3 out. And you're integrating sine, which is negative k over 3 cosine theta from 0 to pi over 2. Negative k over 3. Plug in pi over 2, you get 0. Plug in 1, you get 1. So k over 3 is the mass. M sub x multiplied by an extra y, ky squared. So ky is r sine theta squared, r dr d theta. K is outside. So I have sine squared r cubed. So integrate with respect to r. Sine squared of theta, r to the 4th over 4. Plug in 0, you get 0. Plug in 1, you have 1/4. So take the 1/4 out, and you're integrating sine squared. Sine squared, you might recall from Calc 2, 1 minus cosine 2 theta over 2. Put that in your cheat sheet if you wish. This becomes k over 8. Integral of 1 is theta. Integral of negative cosine 2 theta is negative sine 2 theta times a half by the chain rule. From 0 to pi over 2, plug in 0, you get 0. Plug in pi over 2. If I plug pi over 2 here, I'm taking the sine of pi, which is 0. So the only thing of substance is here. So k over 8 times pi over 2, k pi over 16. Then finally, m sub y, I multiply the original by an extra x. So kxy dA. K comes out, x is r cosine theta, y is r sine theta, dA is r dr d theta. So once again, I have r cubed, sine theta, cosine theta. So I'm integrating r cubed, which is r to the 4th over 4 from 0 to 1. Plug in 0, you get 0. Plug in 1, you have 1/4. So k over 4. Sine theta, cosine theta, d theta. It's a u substitution. If u is sine theta, du is cosine theta, d theta. So it's perfect. So it's just going to be power root sine squared theta over 2. Or to double check, what's the derivative of this? It's this, from 0 to pi over 2. Plug in 0, you get 0. Put the 2 with the 4, that's 8. Sine of pi over 2 is 1. Square it, you have 1. K over 8. So x bar is m sub y over m. K over 8 divided by k over 3 is 3/8. Y bar is m sub x over m. So that's k pi over 16 over k over 3. And that comes out to be pi over 16. K is canceled out, times 3, 3 pi over 16. All right, so final answer, the center of mass is 3/8, 3 pi over 16. All right, so that was section 15.4.